Hi everyone, welcome. Good to see everyone. Glad you could join us. What weekend plans do we all have? I see that some of the folks on the chat have probably some of the same types of weekend plans that I have, which is to sit in my house snowed in. I keep thinking that the weather can't get better or worse in Pittsburgh, and then somehow it manages to plummet beneath all expectations. Anybody not hunkering down? Sounds like a lot of hunkering. Severe snowstorm hurling towards Austin, Texas. I'm always curious, like, exactly how severe is severe? Like, what defines severe? Sometimes it's not too bad down there compared to what we might have here on a weekly basis, frankly. .88 Fahrenheit at 9:30 p.m. is not even fathomable. Well, okay, that's bad enough, I suppose. Tonight we're going to talk about prime numbers, and you might have known that from the title of what we're going to do. And just as a very high-level refresher, what is a prime number? A prime number is an integer, positive integer, that's only divisible by 1 in itself. So, anybody have a favorite prime number? I want to see if anybody's favorite prime is the same as mine. What's your favorite prime? That's my chat warm-up. Couple 17s. Okay. Like 3. I was surprised I didn't see 2 initially. Yeah, that being the only even one seems like it would be a crowd favorite. A lot of 7s. That's a lucky one, I suppose. No one said, well, one person said 13. Adam says 13. Nice. Largest Mersenne prime. I like that. Okay, go ahead and type that one out in the chat. I'll wait. That's some foreshadowing, especially if you've had a chance to go ahead and start doing the practice exercises. Mine is 23. I was disappointed not to see that, frankly, but that's all right. I'll forgive you. We're going to get started with how we might find these things in the first place and how we might, building on what we did last time, come up with algorithms that are fast for doing it and that we can demonstrate are faster than another simpler approach. So last time you might not have thought that something like finding a greatest common divisor could be filled with all these different directions. And so I promise that I'm not going to go as long as we did last time when we talked about GCDs, but my goal for today is to cover prime numbers, do so in a little bit tighter fashion. Thank you for keeping up if you were getting sleepy by the end of the last stream. And my other goal is to get as many folks towards being a 10 out of 10 on how they feel about math as possible, because we're going to have an opportunity to finish up what we're doing with these ancient Greek algorithms and showing how math is sort of a fantastic starting point for any programming course. But a lot of programming courses spend a lot of time on mathematics or graphics or building video games, and these are all really fun applications of computer science. What we're trying to do here is to see some foundational topics that are going to prepare ourselves to be ready to build some scientific algorithms. So once we have what we do tonight, we're going to have a huge amount of the foundation for everything that we're going to do for the rest of the entire course. So we've seen so much already. If you think about where we've started, we've introduced variables and functions. We've seen control flow. We've looked at if statements and while loops and for loops. And then we've started making this transition towards grouping collections of variables together into tuples or lists. And it turns out if you have all of those core concepts, everything that we do beyond now with Python is really just, for the most part, sometimes we'll see a new topic or a new way of organizing the data. But for the most part, we're just taking all those concepts and we're combining them in ever more complicated ways while making sure that we understand exactly what we're doing. So one of the things that we're going to see tonight is that we need to find a way of organizing our code that makes it easy for us to work with and easy for us to conceptualize and abstract what it is that we're doing as our code goes from writing functions that are 8 lines long and think of them as independent and moving towards having functions that call each other and long programs that might be hundreds of lines long. We can make that jump, that leap, because we have the foundation if we start organizing our code in a structured fashion. And we'll see the start of that here at the start of today's stream. So that is, as I said, then we'll be ready to not just take the next steps in terms of programming, but start seeing some scientific algorithms and then give you the opportunity to practice some of those scientific algorithms as well. All right, we should be about ready to get started. I hope you are, because this is an exciting one for me. In the meantime, make sure, as always, please like, subscribe, join PhiloMath for deeper engagement. And I love the chat energy. And please, if you're in the chat and you're a routine participant on our live streams, or not, if you're just following along asynchronously, make sure to join our Discord. So I've got a link to that in the chat. And that's an opportunity for you to continue having this great community that we've started to see in our streams and carry that over to where we're trying to host the community around the clock. So I think we're about ready to get started. As always, thank you so much for joining me. And to get started, you'll notice that what I have here is a collection of pseudocode functions that if you've done our reading from our Programming for Lovers website, you'll find familiar. And I've put them just in a giant doc string of sorts that's going to be treated as a comment, where what we want to do today is implement a trivial prime finding algorithm. By trivial, we mean an approach that would occur to you maybe as the first algorithm you might come up with for finding a collection of all prime numbers up to some integer n. And we're going to compare it against this sieve of Eratosthenes approach from over 2 millennia ago in ancient Greece. I also have some starter code here that's just going to say we've got our fancy 2 lines at the bottom that say run the code in main, and then we have our print statement that's going to indicate the start to our code. So I have this code in a main.py file, and I've got that in a primes folder. So I figured we could just start there. I've also got an animation I would like to show when we talk about this is sieve of Eratosthenes, and I'll show that here momentarily. But in the meantime, let's go ahead and start writing our trivial prime finder algorithm. So I could have a function, and I'm going to call it trivial prime finder, and I might move my pseudocode here so that if you're comfortable with the pseudocode, we'll have access to it as we're writing this function. In trivial prime finder, as always, we're going to be thinking about everything in terms of what are its inputs, what are its outputs, and what are the types of those things. And in this particular case, we might say, well, our input is going to be an integer that I call n, and we don't really need to take anything else. But I do want to return something, and here's where we're able to use what we've learned already about storing multiple variables in one place. So what we want to produce is an array, which in Python we're going to use what's called a list of Boolean values that will store, is this number prime or is it not prime? And I could be more descriptive than that in our documentation string that we're going to have. So I could say, what does this function do? Finds all prime numbers up to and possibly including n. And that's on a very high level what it does, but I probably should specify in the output a little more precisely. So our parameters here are going to be an n, which is an integer, and then the output of the function is going to be a list of Boolean variables, And that list is going to tell us the kth element, or I should say the element at index p will be true if p is prime and false if it is not. And I should say this is a list of length n plus 1, and I'll say whose element at index p will be true if p is prime and false if it is not. So now we understand what it is that we're storing. I'm going to have a list that's a little bit one element longer. So what's nice about this is that I should say i.e. I'm going to call this, I think, prime booleans of p is equal to true if p is prime. Okay. So this way, even though my indexing for my list is going to start at 0, this is going to allow me to say, well, prime booleans of 3 is going to correspond to the prime number 3. Now, for this function, what we want to do first, if you look at our pseudocode here, it tells us what we're going to do. We need to make our list, and then we need to range over that list and check, is this number prime? And so how we're going to do that is I will say, let's declare our prime booleans list, and I can set everything initially to false, and I know how long this needs to be. So from our work with lists, we know how to declare a list that has some initial values, where we know how many values we want. We want n plus 1. We want them all to be false. And then we want to say, okay, this just initializes the length of the list that we want. We do this way because we know how long it needs to be, and we'll see an application later where we don't know how long the list that we want to produce needs to be in advance. In that case, we're going to maybe start with an empty list. But in this case, I know how long the list needs to be, so I'll have some default values built in. And then I'm going to say, let's range. So I'm going to range from 2 up to n plus 1. Remember, we always go one element past the value that we care about. And when we say that, I'm going to say, why do I do this? Well, we know that 0 and 1 are not prime. Okay, so this is why I can safely start my ranging at 2, because automatically prime booleans of 0 and prime booleans of 1 are already going to get this default false value because they are not prime. Now that I've done this ranging, all I have to do is say, well, is it the case that p is prime? And if so, I want to update prime booleans of p to set it equal to true. I don't need to do anything if it's not prime because we've already set default values. So I'll say that's what we're doing with that line of code. And if you've had a chance to look at the pseudocode, you'll know that this doesn't need to be a complicated question, because I will say we are not aspiring to do math in the long term. We're aspiring to be computer scientists. And the difference there, as we've seen before, what's the difference? It's that it's okay to be lazy. In fact, it's admirable. And so what we want to do here is to say, is it the case that this particular p is prime? I could say, if it's the case that when I check that p is indeed prime, and I'm going to use to my point about laziness, I'm going to achieve this by calling a subroutine. So this subroutine is going to return true if p is prime, and it's going to return false if p is not prime. So if it's true, I will set prime booleans of p equal to true. Okay. And then at the end of this process, I'm going to say, once I've had a chance to range over all those numbers, I'm going to return prime booleans. That's my list that I care about. There's one little optimization I could perform here, though. I could say, well, I don't need to test if is prime is true, because if it's not true, even in that case, I'm setting prime booleans of p equal to whatever its value is. So if it happened to be false, I'm doing the same thing. I'm setting it equal to this. So there's one way I can make this a little bit shorter by saying set prime booleans of p simply equal to the value of is prime. So that's what our subroutine function is going to do. As I said, it will take an integer p as input, and then it's going to return true if it's prime and false if it's not. So it's okay to be lazy. In fact, it's an admirable thing to do. We're going to start seeing that this notion of I'm going to write the function that I want, right, which is going to start with an integer n. It's going to give me the list of all primes up to, or I should say it'll give me a list saying whether each integer is prime or not, up to and including n. And to write that, I'm going to start thinking about what would be helpful to me, right? If I had access to someone who is going to write another function for me, and that person sadly is going to be myself, but I could hand this off to them and say, go write this function, test this function, report back to me. Delegation of sorts is a skill we want to acquire in programming, and this is a concept we're going to come back to a lot, and you're going to see all of the reasons why that's the case. For one, it makes our code nice and short and readable, because in this particular case, you simply initialize the list, you range over the values, and you set each value equal to what it needs to be using a subroutine each time. This idea of doing a lot of things by calling a subroutine on each one, something we're going to see quite a bit. But in the meantime, I could write my isPrime function. So I know I want a function called isPrime. And we know that that function needs to take some integer. And just for consistency, I'm going to call it p. And we know that it needs to return a Boolean value. So what does this function do? It returns true if the input integer is prime and false otherwise. Okay, so I'll say my parameters here are p as an integer, and the output is going to be a Boolean, which is true if p is prime, false otherwise. Now, here's an opportunity for us to say, well, one of the things that we might do is to make sure that we're raising value errors. So this is what we've seen before. With a focus on style, we're going to do the same thing with trivial prime finder. I'm going to add a statement that says, what would happen if n is less than 0 in trivial prime finder? That would not be a good thing to have happen. So if we give this negative input to trivial prime finder, I want to raise a value error. And I want to say that there was an error, negative integer given as input. And I want to use a very similar type of value error in isPrime. So with isPrime, I'm going to allow myself to even test p equal to 0. But if p is negative, I want to raise this value error. As for code, what we want to say is, all right, at this point in time, I know that p is non-negative. And the easy cases are if p is 0 or 1. So I'll just say that. If p is 0 or 1, in those cases, we know that the first prime number is 2, so we want to return false. So if p is less than 2, I simply want to return false. Otherwise, I want to allow myself to say, well, we need to check every possible candidate divisor of p. And so to do that, I'm checking a lot of things. Here's my opportunity to use a for loop and to use some ranging. So I'm going to say, let's have a for loop that ranges some variable k between 2 and p plus 1. So this will range from 2 to p. And at every point in time, we're going to say, is k a divisor of p? If so, we're going to conclude that p cannot be prime because we found a divisor of p. And so I will say, well, how do I check if k is a divisor of p? This is a review, so you're starting to see that some of these concepts that we've introduced are going to occur over and over again. In this case, we know how to check k being a divisor of p. I'm going to divide p by k and take the remainder. So I'm going to say p% k. And when I look at that remainder, if it's equal to 0, then the answer is yes, it's the divisor of p. And I can conclude then that p cannot be prime. And I'll return false. This is an example of a type of function that we'll see this kind of category of function quite a bit, which is in order to check if something is true or false, we're going to range over a bunch of values. And sometimes if we find just one, that's enough to conclude that it's true, or in this case, that it's false. And if we survive all of those checks, then in this case, we're going to conclude that the opposite Boolean value has to get returned. So in this case, we know that p is prime. And I can safely return true, because if we had found a divisor, it would have entered this if statement at some point, and we would have already returned false. So that's our default case. Now, we can run this algorithm. We could test is prime. And I think what I really want to do is call this function trivial prime finder. So I'd love to give it a small value and just see what happens, which is what we're going to do. So let's go into main, and I'm going in the wrong direction for main, right? So we're going to go to main, and I'm going to say, let's set n equal to 11. Someone's favorite prime was 11. And so you won the lottery here, and we're going to say, let's say that prime Booleans is equal to, let's call the result of trivial prime finder on n, and then we're just going to print these prime Booleans. All right. And now we're ready to run our code. So the question is, what's gonna happen? Hopefully what we're going to see is two falses corresponding to 0 and 1. And then we're going to see two trues corresponding to 2 and 3. And then we're going to see a false, and then another true, and a false, and another true, false, 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 true, corresponding to each of those integers. So to run this code, I'm going to pull up a terminal. I'm in the Python folder. By default, since it's in my File Explorer, I'm going to cd into the source code directory src that I have, and then I'm going to navigate into the subdirectory primes. Then I'm going to run python3 main.py in order to run my code, and we're going to see what we have. As we can see, our code working flawlessly. This is 0, 1, 2, 3, 4, 5, 6, 7, and so forth. And this is good, right? All these numbers are not prime. So there are 12 numbers, that's right, because the first one's going to correspond to 0. So this is 1, 2, and 3. And that's because we zero-based index our list. So I'm going to have this extra false value corresponding to 0. Something went wrong, did it? No? I thought all these numbers were not prime. So here's an opportunity. Did I trick you by you not noticing this? What are we missing? What did I miss up? Import math? I haven't used any math that we didn't write. All right, we got a good answer. So I'm profiling this as an example of the type of bug that you might see. Say, well, if I look at the top level function, trivial prime finder, I set all my default values equal to false. So probably what's happening is we're not actually setting something that's equal to true. So somehow this is never returning true. And so if I had that hypothesis, one of the things that I might do, I could check it. It appears to be the case, but I could check this, right? I could say print the result of is prime of something that we very much know is prime, 7. And when we print that, you see that false is printed. So we have diagnosed. Here is a very brief glimpse into the type of thing that we're going to talk about later when we have tons of functions calling each other. But and I'm warming you up to the idea that when you have something go wrong, it often makes sense to take your simplest functions, your subroutines that don't call any functions themselves, and test them to see whether they're working. Because if they are working, that gives you an indication that that's not where the problem is. And if they aren't working, well, now you know that you need to focus in on them. So we're missing the fact that we can't seem to find a prime number. And we know that it can't be here because, well, I just put 7 in as my input. So it's not having this error, and it's not raising a value error. So we know that we're surviving down here. But somehow we know that we're always hitting this return false statement. And so the question would be, why is it for a number like 7 that we're always going to, at some point in time, return false? Well, you look at the range and say, there's only 2 other places we could look. We could look here, we could look here. This appears to be right. So we want to check if p%k equals 0. This is like the correct check. So it must be here. And then we say for k in range of 2 to p plus 1, well, we start k at equal to 2. That's good. That's what we want to do. One of the things that might have been dangerous is if I had done this, because then you divide any number by 1 and it's going to give you a remainder of 0. So that wasn't our issue. But then some folks have noticed the problem is you don't want k to be equal to p, because if k goes all the way up to p, then k is going to be a divisor of p, because p is a divisor of itself. So a number, remember, here's where we know our definition. A number is only prime if its only divisors are 1 and itself. Not 1 and 2, 1 and itself. So I can fix this by saying I don't want to check p itself, and this will allow the ranging to stop at p minus 1. Now when I save this, I can rerun our program, and we see that is prime of 7 is now returning true, and our prime Boolean list appears to be good. So that's 0, 1, 2 is prime, 3 is prime, 4 is composite, 5 is prime, 7 is prime, and 11 is prime. So far so good, and we could test this on larger values, but I think we're in good shape. The unfortunate thing is that the phone is ringing. The phone is ringing and the mathematicians are calling yet again. So there is something that they're going to say, which is, I don't think that this is really a fully fair trivial prime finding algorithm. I think if you're going to compare something that's more advanced to this, it's going to tell you that that algorithm B that we're going to write is going to be way better than this algorithm, when in fact we're missing something that will make this algorithm much faster that we need to add to it. Does anybody see what it is? What can make this faster without changing very much about our algorithm at all? We've got this trivial prime finder algorithm, and I'll give you a hint. We can make is prime faster. What can I do? Iris says squirt of n. Good. So we do need to use a squirt. And one of the things that you might think is, oh, I don't need to range up as high. P over 2 is one thought. But I want to present just a little bit of math here, just a little bit, which the math I want to tell you is if P, some integer, is the product of K and, I don't know, some other integer B. And you can safely assume that one of these has to be less than or equal to the other. Okay, so consider the smaller integer K as part of that product. Then K is less than or equal to squirt of B. And by squirt we mean square root. You might say, why does that have to be the case? And there's an opportunity to explain why this is. And we can use a very short, what's called proof by contradiction. We have an example of proof by contradiction on our Programming for Lovers website in the reading. But here's another tiny example of it, which is assume that this weren't the case. Assume that like K were greater than square root of P. So somehow you'd have a product that's equal to P, and then both numbers are going to be greater than square root of p because b is at least equal to k. So b is also bigger than square root of p. Well, that would be really weird because when you multiply them together, when I do k times b, which is equal to p, that would be greater than the square root of p times itself, because both k and b are greater than square root of p. I don't know why I can't write greater than today. So both of these numbers would be greater than the square root. So when you multiply them together, they're greater than the square root times itself, which is equal to p. So we've shown that k times b is greater than p, which is clearly not true. So this cannot be. And by this, I mean this statement, k greater than square root of p cannot be true. And so we know that k is less than or equal to square root of p. This means if we're looking for things that might multiply together to go into p, to give us the resulting product that's equal to p, well, I only actually need to consider all the numbers up to square root of p. Because if I don't find anything up to square root of p, I'm not going to find anything past that. Because if I did, it would have to multiply by a number that's smaller than square root of p, which we would have already found. So there's this clever idea that we don't actually need to go all the way up to p minus 1. We don't even need to go to p over 2. We just need to go up to the square root of p. And that's going to make things much faster when we run is prime on a huge number, because we're not going to be running all these comparisons all the way up to p minus 1. Imagine, for example, I don't know, p is equal to 10,000. Before we were going to go up to 9,999. Now we're going up to the square root of 10,000, which is just 100. So that'll be much faster. There's one thing that we do need to point out, which is I want to make sure that I import math. And I need to call this square root function from the math module. To do that, I'm going to say, when I check that I'm going up to p, but not including p, I need to go up to, but possibly including the square root of p. So here's where we want to make sure that we're not doing something dangerous. Like if is prime takes, I don't know, 100 as an input, then we want to include k, the case where k could be equal to 10. So I don't want to go up to, but not including 10. I want to include it. So I'm going to add 1 to that result. And now we're ready to rerun our code. And when we rerun our code, so I've saved it, then we hit the up arrow to give us python3 main.py, I get an error. And what we see is a very rare example of Python being strict about types. So Python says, in range, this has to be an integer, and this very much has to be an integer too. So you're saying what you have given me is quite possibly a float. When you call the function math.squareroot, the result of this is going to be a float or a decimal number. But I want this to be an integer. And so we will use something, the fix here is fortunately very straightforward. There's two possible things we could do. One would be what's called casting this number, math.squareroot of p, to an integer. So in the case where you have a decimal and you add this int function around it, it will round that positive decimal number down. So if this happened to be like 2.781, it would round it down to 2, okay, which is what we want to see. So this now will fix everything. When I save this and run it, we'll get the same result as before. So this was our correct collection of true and false values corresponding to the primes, and then this was our is prime of 7 value. If it turns out that this is an integer, but it's just represented as a float, like in the case where p was 100, well, your square root is still going to be 10 here, and it's just going to be the integer version of 10, and then you add 1 so that you make sure you don't leave 10 out when you perform the range. And all is right with the world. There's one other thing we could do, which is I don't need int at all. Technically, if we look at the math package, there is another function called isquirt, I-S-Q-R-T, which goes ahead and does the integer casting for you. So it finds the integer that is the largest integer less than or equal to the number that you gave it as input. All right. So you don't need to necessarily know that. And you could, it's another example of the sort of thing where, is that helpful to us day to day? Not really. You don't need to be an encyclopedia of all the different functions you could have. And so I'm just going to make this int of math.squirt of p. All right. So that's our trivial prime finder. And that's how you might think about, at this point, up to this point in the class, if I just said, find prime numbers for me, this is probably how you would do it. You would say, I'm going to make a list of false values. I'm going to range through that list, and then I'm going to check, is this number prime? If so, I'm going to set the corresponding value of the list equal to true. So far, so good. What we want to see is how Eratosthenes did this over 2,000 years ago. And the nice animation for Eratosthenes' approach, I'm going to show it in an animated GIF. And it's actually something that even in a public elementary school, I learned as a way of finding prime numbers. What's nice about it is it's very visual, and it can involve colors and these sorts of things. I'm actually curious if you did this yourself when you were in school, if you learned about prime numbers this way, let me know. We start by the number 2, and then the idea is you cross off all the numbers that are multiples of 2. So you cross out all the even numbers. Then you look at the next number, which is 3. You cross off all of those. You skip 4 because it's already composite. So the next number is 5, and you cross off its multiples. The next number you haven't crossed is 7. You cross off all of its multiples. And then you reach this point where the remaining numbers here that are in gray are all getting colored magenta. All of those numbers we know are prime. And the reason why is by the same argument as before. So this number 120 has been chosen in a very special way because it's 1 less than 121, and 121 is 11 squared. So the square root of 120 is like 10 point something, but it's not quite 11, which means if I'm trying to find, does a number have, is a number the product of two numbers that are not itself in 1? Well, I only need to check the possibilities up to the square root of 120, which means I only need to check everything up to and including 10. So we'll see this one more time just walking through the GIF. We cross off 2 and all of its multiples. Then we look for the next gray number, which is 3. Cross off all of its multiples. Skip 4. Next gray number is 5. Cross off all of its multiples. 7, which we know must be prime. Cross off all of its multiples. And then 8, 9, and 10 are all composite. So everything past this that survives this process is gray. If you're wondering, where is that GIF? This GIF has been on Wikipedia for like my entire adult life. They've never made a higher res version of it. It's never really been updated. It's kind of like, when you achieve perfection the first time, you don't need to continue updating it, which is nice. It's refreshing. They could change the fonts or the colors, but yeah, it is what it is. The question is, this is an idea that, I remember being taught at the age of like 10 or something with literally a sheet of numbers, a table of numbers up to like 100. And we crossed off all the multiples, and then we circled everything that was left. If the algorithm is understandable or teachable to children in that way, certainly we must be able to take this idea that Eratosthenes had and convert it into an algorithm, and then we're going to do the important work of timing it against the trivial prime finder. But we're going to keep this visual in mind, and then we want to implement it. So I'll just say the easy part that we know we can do is to, copy in, take what we've already done here, and maybe near main, I'm going to call this sieve of Eratosthenes. It's still going to take an integer n as input. It's still going to return a list of Boolean values. It's still going to find all prime numbers. I'm going to say using Eratosthenes approach from ancient Greece. And this is still going to be what we return. Okay. The only difference is that, well, we're doing so with what we hope to be a faster algorithm. And our hope for why this might be faster is that we're not checking each individual number and treating it as an independent notion. We're going to go ahead and pre-compute a lot of the values of the table. So I only need to go up to like square root of n, so to speak. And everything past that, it will have already been crossed off as the multiple of something. So we cross off all the 2's and the 3's and the 5's and all the multiples of 7 and so forth. And then once you've done those simple tasks, then you know that the remaining numbers must be prime. I don't need to call a subroutine on them. I can just go ahead and conclude that. So it seems like a pretty approach. It also seems like a fast approach. And the question is how to implement it. So like before, we have the same inputs here, the same outputs, the same value error. But then the question is, I want to have a prime Booleans list that's going to represent the primality of each one of these integers. And we know how long it needs to be. It needs to have this length n plus 1. Except that when we look at how the sieve starts, everybody is gray at the start. So I'm going to start gray, in other words, especially when you think about what happens when you look at 3 and then 5 and then 7 and so forth. And also what happens after you've crossed off all these multiples. Gray means that it is prime. So if we're starting the sieve off as gray, well, what I should start everybody off at is true. Except I have these extra values corresponding to 0 and 1, and they're definitely not true. So I should also say, okay, 0 and 1 are definitely not prime. So I'm going to set prime Booleans of 0 is equal to false, and the same thing for prime Booleans of 1. Right. There's a little bit of a danger, I suppose, that if somebody gave me n equal to 0, I would have a problem here. Although, no, I suppose that's okay. All right, so we would have, no, we'd only have length 1. So let me say this, less than or equal to 0. I'm just going to call this invalid. All right. So very minor point there. In the meantime, once we've set that 0 and 1 are definitely not prime, at the end of this process, I want to return prime Booleans. So that's the list that I have that I'm eventually going to return. Now we say, what's the next thing that we do in the sieve? The very next thing that we do when we look at the picture is we cross off 2. Okay, so crossing off 2 for the multiples of 2 means setting them to be composite. So all these multiples are all composite, but this 2 itself winds up being a prime number. So in other words, when we see a gray number, a number that has not been crossed off, we're going to set it to be a prime number. And then we want to cross off all of its multiples to not be prime. We want them to be composite. So what I'm going to set is the first, after I've set prime Booleans of 0 to be false and prime Booleans of 1 to be false, I'm going to start building this engine that's going to say for p in a range starting at 2, because I'm going to start off with the number p equal to 2. And remember, how far up do I need to go in terms of checking the multiples of a number? Well, in this particular case, I said by the same rule as before, two numbers multiply together to give you something up to 120. One of them has to be less than 11 because the square root of 120 is 10 point something. So when we do our ranging is going to start p equal to 2, and it's going to be the same thing. I'm going to say, I'm going to go up to the integer version of the math.squirt of n, and then I'm going to add 1 to that, and that's going to allow me to say p can go up to and possibly including the square root of n. So I'll say range p from 2 to square root of n. And as we do this, then I want to say, well, cross off the multiples of P. And you might imagine when you've arrived at P, when P is equal to 2, it's already set to be prime. So that's good. The other thing I want to point out is it's tempting to say, well, we're going to say P is equal to 2, and then P is going to be equal to 3, and then P is going to be equal to 4, and then P is going to be equal to 5. And at each point in time, we're going to cross off all of the multiples of P as composite. Except there's a nice insight here. I think it's clever insight number 1, which is as I range through this, I'm going to first cross off all the multiples of 2. Great. Then I'm going to cross off all the multiples of 3 after I do this. Great. But I don't cross off all the multiples of 4 because I don't need to. If it's divisible by 4, it's divisible by 2. So then the question is, why would I do this? I don't want to necessarily set P equal to 4 and cross off its multiples. So when is it that I do want to cross these off? I cross off the multiples of P as composite if ... What condition holds? When will I cross those off? If P is prime. Good, Aisha. Excellent. So if I know that the number is prime, then I want to cross off its multiples. If I know that it's composite, like in the case of 4, what we saw before, then we don't need to cross those multiples off. So one of the things that I could imagine doing is to say, I'm ranging over all these P's. I'm going to check, is it the case that P is prime? And if that's the case, well, cross off the multiples. And we can talk about how we could go about doing that here shortly. However, that's missing something. This is missing something. What is it missing? There's going to be one more very clever insight into making this algorithm work. What is this algorithm missing? I'll give you a hint. When you arrive at P, you know to cross off of its multiples if it's gray. Okay, so we know to cross off the multiples of 3 or 5 because when we encounter them, the number in the table is gray. What does it mean for the number to be gray? The value here in the table is going to be gray if, I see it in the chat, good. If it hasn't been crossed off yet, and I know that a number has not been crossed off yet, if we can just check its value in the table. So the problem with this statement, in other words, is it's going to call this subroutine. And so this is going to make it no different to the algorithm that we had before. The algorithm we had before is going to call is prime in a bunch of cases. This is going to call is prime in a bunch of cases. But if it's prime, I know if it's prime. I don't need to check if is prime if P is equal to true. I'm going to check at this point in time, is it the case that when I look at prime booleans of P, is that prime booleans of P value equal to true or not? And if so, now I'm going to cross off the multiples of P. Okay, so think of this as a gray value in the table. And if you see a gray value, I'm going to cross off the multiples of that integer. So now we've updated our code, and I'll show you one little stylistic thing, which is that in any language, if you'll see this statement a lot. We've seen it already in this course a few times, which is if some statement is equal to true. You don't need to check the equal to true. So stylistically, and you may not be comfortable with this yet, but stylistically, I'm going to start writing my if statements when I'm checking something equal to true. I'm just going to have if prime booleans of p, because if this is true, well, it will evaluate this to true, which is good, and then it will enter the if block, which is what we want. Then the next question is crossing off the multiples of p. Okay, that seems hard. It means I need to range through the table in some way, and I need to identify precisely the numbers that are multiples of this integer p. What do I want to do? I want to be strong at computer science. So that means I need to be lazy. And to be lazy, that means I'm going to use a function that I'm going to delegate this work to help us out. Okay, so in this case, what I'm going to say is if prime booleans of p is equal to true, I'm going to update prime booleans to be the result of crossing off a bunch of multiples. Geez, what should I call such a subroutine function? I'm going to call it cross off multiples. And what does it need to know? It needs to know what does your current table look like, and what multiples do you want me to cross off, which in this case is p. So in each step of the algorithm, if I'm at a gray value of the table, I'm going to cross off the multiples of this particular value, and I'm going to update the table to be equal to the result. Then it's just a matter of writing this cross off multiple subroutine. So I've kind of described what this subroutine is going to do, but we know it's going to be called cross off multiples. And I'm going to say, let's keep everything consistent here. I'm crossing off the multiples of an integer. And that's the second parameter here. So I'm going to say prime booleans is a list of bools. So we know that that's just a list of true and false values. And the integer is going to be p. And the result of this is going to be a list of Boolean values as a result. Okay. So here's where I can say on a high level what this is doing is this crosses off all the multiples of a given integer in a prime, I should say in a table holding the primality of integers, collection of integers, between 0 and n plus 1. That's like visually what this function is doing. If we think about what the parameters are to it, well, we have prime booleans is going to be a list of bools. And we're going to have p, and that's going to be an integer. And then what's the output going to be? It's going to be a list of booleans. And it's going to correspond to setting every multiple, setting prime booleans of, let's say, k equal to false for every integer k that is a multiple of p. And what's nice about this is I cannot stress enough the value of a doc string, because just thinking through stating what the function is going to do is going to make writing that function so much easier. First off, of course, I should probably have a quick check in terms of what might cause a value error. In this case, I could say, well, if I'm probably not going to like this if this prime booleans list is short, or if the p-value that I'm going to be taking as an integer input is less than 2. So I'm going to have a couple tests here, which is if p is less than 2, then I want to raise a value error, and I want to say that the value given was too small. Okay, so we're only going to be crossing off p equal to 2 or bigger. And similarly, if the length of this prime booleans is going to be, I think, less than 2, I'm going to say, let's raise a value error and say error prime booleans list too short. Okay. And that might be very useful In the meantime, at the end of my function, I know I'm going to return prime booleans. Okay, so after I perform this update, that's what I'm going to return. So this is the, I should say maybe this is the updated version of prime booleans corresponding to setting these values. So all I'm doing is going through and I'm setting these values, and then I'm going to return it. So way down here, that's what I'm going to return. In the meantime, then it's just a matter of range over all the indices of prime booleans that are multiples of p and cross them off. Okay, so this is the case of, regardless of what our p is, 2, I'm crossing off all the multiples of 2. 3, I'm crossing off the multiples of 3. 5, I'm crossing off the multiples of 5. So I can imagine what I need to do then is start my value of k somewhere and range it up to something. So in this particular case, I could say what we don't want to do is set that equal to p. Okay, I could trick you if I wanted to, but it's a completely valid thing that we might think about doing. I don't want to cross p off. So if k is equal to p, the last thing I want to do, and I'm going to fill this in shortly, but when I say cross off a number, what I mean is I'm setting prime booleans of k equal to false. This is the same type of trap as before, where if k is equal to p, and then I set prime booleans of p equal to false, that's not good, because if I'm crossing out the multiples of 2, I want it to stay prime. It definitely needs to still be true. Same thing for 3. So I don't want to cross off 3. So instead what I'm going to do is I can start it at the next integer. So that's fine. So what I'm going to say is I'm going to start with p plus 1. I'm going to go up to, and possibly including the end of the list. Okay, so the last element is n. So for example, if we went up to 121, I would eventually cross off this element too. So we're going to go up to the very final element of the list, and I'm going to say, is it the case that k is a multiple of p? So here is where this is going to get indented, because I'm going to have an if statement that says if, well, what does it mean for k to be a multiple of p? That means that p is a divisor of k, and we know how to check this. It's the same thing we've been doing before. So I'm going to say k percent p, k is percent p is equal to 0. And if that's the case, then I'm going to set prime booleans of k equal to false. So this means that p is a divisor of k, which means that k is a multiple of p. Everything is good. The question is there a better way? Like, is there something in this ranging that we could improve? And I'll give you a hint. If you were doing this by hand, what would you do? Like if I were crossing off, imagine I'm a school child, I'm crossing off the multiples of 3. What do I actually do? Or 5. Iris, thank you, good. So you're saying you would just skip numbers, right? So if I'm crossing off multiples of 5, I go 5 plus 5 plus 5 again plus 5 again. I wouldn't be checking if 8 is a multiple of 5. I don't need to. I'm just going to go 5, 10, 15, 20, 25, 30, and so forth. So this is a little bit unnecessary. And what's nice about Python is we can just set a step size equal to p. We can start at the first number that we might know is a multiple. And a lot of folks are telling me, don't start at p plus 1. Start at the first multiple of p. That's not p. It's 2 times p. And you're still going to go up to n plus 1, but you're going to skip with a step size of p each time. So if I'm crossing off multiples of 2, every time through the loop, I'm going to add 2. to k. If it's 5, I'm going to add 5 to k. And in general, I'm adding p to k each time through. That's the same idea as jumping over. So for the multiples of 2, I'm jumping over one number. For the multiples of 3, I'm skipping 3 each time. Now, I don't even need to check that p is a divisor of k, because is it the case that k is a multiple of p? Yes, I skipped straight to the multiples. And so I don't need to make a check. I can simply set prime booleans of k equal to false, and I've crossed it off. Once I've done all this ranging, I simply return the list, and my function is done. So we're in good shape. We've actually implemented the entire sieve, because the sieve we wrote on a high level with our sieve of Eratosthenes function. And this function calls one subroutine that we wrote called cross-off multiples here. And we just finished writing that. So what should we do? Well, we should probably pull up a terminal and make sure that our code is saved. And we're going to run Python 3, or Python if you're on a Windows machine, main.py. Okay. Oh, this was supposed to give an error. All right. So in this particular case, this is, oh, it does not give an error because I haven't called it. Okay. I was trying to trick you. So I have tricked you. Okay, let me tell you. I have tricked you, I promise. But I didn't actually have a chance to trick you because I didn't call the function. So that's why nothing went wrong when I ran it. But I'm going to tell you that something is supposed to go wrong. And so when I call sieve of Eratosthenes on n and call this function, okay, now we run it. Oh, and now I get my error. Okay. So the trick here is when I ran sieve of Eratosthenes, and it's telling me on line 140, n is not defined. That's perfectly reasonable for Python to tell us that, because within this function, you don't see any definition of n, right? So the question is, what is n? N is the max number that I want, right? But all I have is this prime booleans list. So the question is, how do I become n? How do I obtain n from this list? Certainly I can't get it from p. We need something that's going to say, make sure that n is declared. We need to use length. Okay, so is it n equals length of prime booleans? Ooh. Sounds like that might be a little dangerous. Remember that we know that the length of prime booleans is equal to, the length is equal to n plus 1. Okay, so they're not quite equal. And so we have to do some dreaded algebra. And that dreaded algebra is going to tell us that the length of prime booleans is equal to n plus 1. And so that means that length of prime booleans minus 1 is equal to n. Okay, so n is equal to length of prime booleans minus 1. And now everything will be right, I hope. And when we save it and we run it, we're not going to get an error. And here is the sieve collection of results. And you'll notice that I hope it matches what we saw before. So we'll get false, false for 0 and 1. Then we get true, true for 2 and 3. Then false for 4, true, false, true, false, 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 true. And it's matching. And we, of course, should call this on larger values. But for now, it seems like everything has been going well. Now we get to do the exciting part, which is to say, how much faster is this cross-off fancy approach from Eratosthenes? How much better is it against our trivial approach? What we saw when we did this for GCD algorithms was the improvement was shocking. Euclid's algorithm was not just simple to perform, but it was an amazing speed up over what we had before. So let's look at the primes, the case of primes, and do the same thing. So in main, I'm going to say, let's time these things. Let's set, for example, n, well, I'll update the value of n to be like 10,000. So we're going to find much larger primes. And I'm not going to print the results of finding the primes. That's going to consume a lot of the terminal, but I am going to run the functions and I'm going to see how long they take to run. This is the same sort of thing I mentioned when we looked at GCD algorithms. It's the same sort of thing that we've seen before that we're going to see throughout the course. Anytime you want to time something, well, I can go to where my import statements are and I can import time, and that's going to allow me to implement this like abstraction of a stopwatch. And to do that, I'm going to go into main and say n is 10,000. I don't want to time that. I'm going to say that start is this variable called time.time. And then I'm going to run trivial prime finder of n. I'm not going to store it anywhere. I'm just going to run the function. Then I'm going to stop the watch. So what we're doing here is timing the two algorithms. To stop the watch, I'm going to set some variable, let's call it elapsed trivial, equal to the current time minus the start. And then we're going to say, all right, let's do the same thing. Actually, I should print something nice. So we're going to use this F string that says trivial prime finder took, and then I'll say I'm putting the elapsed trivial variable into braces, and we're going to say seconds here. The other thing I'm going to add is round it off to 6 decimal places, so I'm going to have a colon dot 6f, and then I'm going to do the same thing for the sieve of Eratosthenes. So n has already been set. I'm going to set start is equal to time.time. I'm going to call the sieve of Eratosthenes on this input n, and then I'm going to say how long did the sieve take. It took what the current time is minus what the time was when we started. Then I'm going to have the same sort of fancy print statement that says that the sieve of Eratosthenes took elapsed sieve. Okay. And I could run that, but remember from before, we probably want to do one extra thing, which is to say, we're going to study this on a variety of different inputs, and to compare two runtimes, when you imagine that the inputs could change, we want to take the ratio between the two runtimes, and so we call that the speed up. So the speed up is how long did the trivial algorithm take, because presumably that's the slower one, it's going to take more time, and how long did the sieve take. So we divide the elapsed trivial by elapsed sieve. And now I'll print this in a fancy way too. So we're going to say print f. The speed up in this particular case is, and then I'll put the speed up variable into parentheses. We're going to print it with 2 decimal places of accuracy. And then I'm going to say that it's x faster. So we can save our code. And here's our opportunity to run. Before I run it, and before you run it, my question would be, give me a value. What do you think the speed up is going to be when I run sieve of Eratosthenes versus trivial prime finder for n equal to 10,000? How much faster as a multiple do you think sieve of Eratosthenes is going to be? We have an immediate answer of 432.1. I'll be impressed if that's the exact number. What do we think? Okay, so we got everything from 5 to 430. And everything in between. I like that there was some reasoning behind this. So BZ says, look at the square root of 10,000. Somehow that might be because we're not, instead of going all the way up to 10,000, we're kind of doing a number of operations up to the square root of 10,000. Okay, so that's a reasonable answer for 100. Let's see. So I'm going to run the code. And what we see is it's not quite that perfect. So we have a little bit of extra work that the sieve of Eratosthenes is doing, but there definitely is a speed up. So it's about 14 times faster in this particular case. Now, that having been said, we don't necessarily care about the speed up, right? For a single value when we're comparing two algorithms. What is it that we care about in terms of when we're looking for a speed up of an algorithm? This is a refresher from when we looked at GCD algorithms. What is it that we really care about? Consistency for all inputs from Yasmin. That's a good point. Now, for example, with GCDs, you want to make sure that these work for numbers that are different sizes or numbers that are similar, a lot of different inputs. For prime finding, the algorithm is the algorithm. There's nothing special about 10,000 versus 10,001. More inputs in general is a good observation, but more inputs of what kind? Remember, when we do computing, we want to do computing on what types of inputs? What's the benefit of having a computer in the 21st century? There we go. We want to run it on more and more complicated data, which for the case of a single integer is what? Make that integer much larger. Try it on small numbers. So let's see what happens at 10. I don't even know what's going to happen at 10. It actually was faster. I don't know how much I trust that. Sometimes you run an algorithm and when the runtime is very small, it's hard to trust it. But yeah, what we care about is how does the speed up change over time? What we saw last time is when we look at the study of an algorithm and we think that it's faster, we care about how much faster it is, not just for small inputs, but as those inputs get larger and larger. So we've seen that at 100, it's about 10.5 times faster. At 10,000, it's about 15 times faster. At 100,000, it's about 23 times faster. And then at 1,000,000, we get a little bit of a wait time. So the trivial prime finder here is taking 1.54 seconds, and sieve Eratosthenes is taking 0.03. In general, like a 50x speed up is really worthwhile. What we would like to do, I'd like to add one more. I'm not going to add one more zero. I'm going to at least take us to 2 million, because then it's going to actually take the trivial prime finder like a minute to run. So we're going to be sitting here waiting on it to finish. And I don't want to do that, but I will show you that, well, in this case, I multiplied it by 2. You see there's a little bit of like stochasticity here, but for the most part, when we run the algorithm for larger inputs, we're getting a greater speed up. It's also so it's growing, but it's also not growing like it did for the Euclid greatest common divisor algorithm that we saw, where it was taking something that was taking multiple seconds and it was still doing it in like 2 times 10 to the negative 6 seconds, right? So the speed up that we were getting before was dramatic. And as n was increasing, it was getting more and more dramatic. This seems to be much gentler, much more gradual in terms of the speed up. So it might make you wonder, they're still finding prime numbers. And then the question is, even though we've seen that Euclid or Eratosthenes' algorithm is really neat and obviously provides a speed up, it's not in the grand scheme of things that much like a dramatic improvement over how you might find this with the first trivial algorithm that we might come up with. So because it's that, yeah, Robert, exactly, it's that small speed up comparatively, it might make you wonder, how is it that we find prime numbers today? Like, they're still finding these big prime numbers. How is it they're finding it? That's where I want to get to here, just to wrap everything up. There's a couple other things in order to get there, though, that I want to talk about. One of those things is, I look at this and I think, well, did we really find the primes? Kind of. But we are listing these out in kind of an ugly way. So there's something dissatisfying about just listing false, false, true, true. Why don't we list the primes themselves? And so we know, we have good evidence that the sieve of Eratosthenes is the faster algorithm, which means anytime I want to get all the primes up to n, I'm going to use sieve of Eratosthenes. And so, for example, if I were to want to write a function called like list primes, and it still takes an integer, but this returns not a list of Boolean values, but a list of integers, and I can specify what it does. So what list primes is going to do is it returns a list of all primes up to and possibly including n. So in terms of parameters, it takes an integer n. And in terms of output, well, it's going to be a list of integers, and this corresponds to the list of all primes up to and including n. Okay. So in this case, I might say, here's an opportunity for a value error. So if n is less than 0, that would be bad. I don't want to list all the primes up to -3, so I'll raise a value error in that case and say error, negative integer given. And if we make it here, everything is okay. So I don't know the length of the list in advance. Here's one critical difference from what we did before with sieve of Eratosthenes. Before, I knew exactly how long my list needed to be. I'm trying to find it. Okay. So when I set prime booleans in sieve of Eratosthenes, and the same thing for trivial prime finder, I knew exactly how long that list needed to be. It needed to be of length n+1, where n was the input integer. But one of the things I can't tell you just right off the bat immediately is if you gave me n equals 2 million, how long does this list need to be containing all the primes up to 2 million? That's a harder question for me to answer. So as a result, we're going to do something that we're going to see throughout the course, which is sometimes I don't know how big the list is going to ultimately be. And that's okay, right? I'm good enough, I'm smart enough, and it's all right that I don't know how big that list is going to be. So if I don't know how big the list is going to be, let's just set it to an empty list. And I think we could also say, or you could just do list parentheses. But I like just having brackets. And way down here, I'm going to say we're going to return prime list. That will be how the function will end. In the meantime, what I would like to do is, I'd like to categorize all the prime numbers that I find. So here is an opportunity for us to not do what a lot of beginner programmers might think to do, which is, oh man, I've got to write more code to find the prime numbers again. No, we already have code to find the primes. Okay, so let's use it. So I'm going to say we have a way of getting all of the primes. They're just in a format that we don't necessarily like. So I'm going to call sieve of Eratosthenes of n. And that's going to give me my true and false values, right? So then it's just a matter of saying, range through this list and identify which ones are true, because those are the primes. So I'm just going to say for p in the range over, well, what do I need to range over? I'm ranging over the length of prime booleans. Okay. And technically there is a 0 here, right? This is the standard way of ranging over a collection of elements in a list, is to say we're going from 0 up to, but not including the element at index length of prime booleans. That's because we know from before, remember, that the final element in a list has an index equal to the length of the list minus 1. So this is always very convenient that we know that we're going to range over a list. We go from 0 up to the length of the list. And we also know that Python gives us the shorthand that I don't even need to put the 0 in there. Once we perform this ranging, I'm going to just check. Is it the case that prime booleans of the current integer that I'm looking at, p, is that equal to true? And remember, I don't need to check if something is equal to true. I can just check if it is. That will give me a true or false. And if so, well, append the current number to the list. And so I will say, I've identified that it's prime, and I'm going to say prime list dot append p. And that's it. That's all I have to do. So having written the sieve makes my work really easy here. I also want to use the opportunity to show you a shorthand technique for what we're doing here, which is we are ranging over this list. But as I range through the list, I care about two things. I care about the value of p. You'll notice that's important because it's telling me what the current index is, which tells me the current integer. I also care about whether or not it's prime or not. So I care about the value, prime booleans of p. And the shorthand trick, we saw a shorthand trick for ranging over just the values of a list last time. This time we're going to have a shorthand trick that ranges over both the indices and the values of the list. So there's a way of doing this by saying for p, comma, whatever the value is. And the value here is a Boolean variable, so I'm going to say, I'm going to call it is prime to represent that value. And then instead of ranging over it, I will say we use the function enumerate that we apply to prime booleans. Now that I've done this, I can check not if prime booleans of p is true, but is it the case that is prime is true? If you like the other way of writing the function, it's absolutely fine. You can go back to that. I don't mind. But this is a nice shorthand trick for Python in general. So this gives me the indices. This gives me the values as I go. And so I'm checking, is it the case that the current value is true or false? And if it's true, well, I want to append p to the list that I'm creating. Now we can run this, and in main, I've got my timing. Let me dial down some of my timing a little bit here. But after my timing, I might say, let's call prime list, set a variable prime list equal to list of primes. I'm going to go up to my favorite prime number 23, and then I'm going to print the result of that prime list. And when I save this, and then I run it, python3 main.py, I see all of the primes between 2 and 23, which is prime, and everything in between. That's item 1 we might do. Item 2 we might do would be to answer another question, which I think is a very natural question anytime we're doing something with math. And that question is, how many? In this particular case, here's my question to you. How many prime numbers are there? How many primes are there? Two very, very different answers of infinite and natural log. Okay. Good. So the answer is infinite. Good job to those who said infinite. And the reason why? Well, there's a proof of this. So, good. Some other people are saying it's an established mathematical truth. We've got the proof of it on our Programming for Lovers website. And there was a famous mathematician, which means not at all famous, because he's not top 5 all time, but Cambridge mathematician Hardy from the 20th century, who wrote a treatise about the fact that all humans should see 2 proofs at some point in their life. One is that the square root of 2 is an irrational number, and the other is that there's infinitely many prime numbers. So if you want to see that proof of the fact that there definitely are 100% infinitely many prime numbers, that's part of our reading on our Programming for Lovers website. Make sure to check that out. My question for now is, how many prime numbers are there that are less than or equal to n? So is there a formula in terms of n that would apply to say, oh, well, if you're looking for the number of primes up to 23, it's some function of 23. If you're looking for it up to 2 billion, it's a function involving 2 billion as an input. Yasmin said, now I get to say natural log of n. So you could just say eventually natural log's got to be the answer to some question in the class, I would hope, right? Let's see. So what I would like to do is, let's do something without doing a whole lot of additional math, right? Let's plot all the primes up to n, okay? So here's an opportunity for us to do a visualization. I'm going to have n on the x-axis, and on the y-axis, I'm going to be how many primes have I encountered up to that value of n. So in order to plot this, here's where we want to pull in some existing code for plotting. And it's an opportunity for me to say something nice about Python, which is that Matplotlib is nice. It's good. It's very useful. If you have an example like this, where I know pretty much precisely what it is I would like to plot, it will be very lightning fast at making you a very simple plot. And I'm going to show you that here to finish things up. The first thing I need to do, though, is write another prime-related function. And that prime-related function that I need, and I'm going to move this up a little bit so that it's before main. The prime-related function that I want to have is called prime count array. And this is going to take an integer n as input, and it's going to return a list of integers. And let's specify what it does. So this is going to return, as I should say, this produces a list storing the number of primes encountered up to a given integer. So I can be more precise by saying my parameters here are of course going to be n as an integer, and my output of the function is going to be a list of integers. And I'll say this is a list whose kth element is equal to the number of primes less than or equal to k. And I should say this is also a list having length n plus 1. So I'm going to do the same thing where the index, the element at index k is equal to the number of primes less than or equal to k. So this is going to correspond to the current integer. Okay. So I might say if n is less than 0, that's obviously bad. So we're going to have another raise value error and say negative integer given. In the meantime, I want to say I also definitely want to collect all the prime numbers. So what am I going to need? I'm going to need the sieve. So let's say prime booleans is equal to the sieve of Eratosthenes of everything up to and possibly including n, and that's going to give me those true false values. So first, get all the primes as true or false using the sieve. And then next I can say, let's make the list. So the list that I care about is going to, as I said, say the element at index k is going to store the number of primes less than or equal to k. So in this particular case, I know how long this list needs to be. It's going to have length n plus 1. I know it's going to be integers. So I'm just going to start everybody as equal to 0. And we know how to do that as well. So in my function, I'm going to say the result that I care about is equal to a bunch of zeros, and n plus 1 of them to be precise. And then eventually that's the thing that I'm going to return, which is that list of integers. In the meantime, what I want to do is keep track of how many primes we've encountered. And when we start the algorithm, we have encountered 0 primes. That's not going to be a surprise. So I'm going to have a prime counter that I start off as equal to 0. Then I'm going to range over what I've just made. So I'm going to say range over the list of primes. And to do that, I'm going to say for I in range over length of the prime booleans. Okay, so again, the standard way of ranging over every element in a list is just range over 0 up to the length of the list. And we don't need the 0. So now hopefully we're getting comfortable with that syntax. I'm going to say is prime is equal to prime list of I. Okay, and here's another opportunity for me to say I want to range over the whole thing. I care about both values. And so here's an opportunity for me to say for I is prime and enumerate prime booleans is what I care about. So is prime is equal to prime list of I is no longer needed because that's the current value that I care about. In this particular case, I'll say is the current number prime? So is it the case that is prime is true? Meaning if is prime is true, then what I want to do is I found a prime. So update the counter. And I'm going to say prime counter equals prime counter plus 1, which we know the shorthand trick for, right? So at this point, we should be comfortable in saying if I'm just adding 1 to a variable called prime counter, I'm just going to say prime counter plus equal to 1. And this will allow me to keep track of everything, regardless of what index I'm at in my prime booleans list. I want to say set the current value of my list equal to the number of primes. A little hesitant to put another hashtag in there. The number of primes encountered thus far. And I know what that is. It's the prime counter. This is why I'm keeping track of it. So I will say result of I is equal to the prime counter. Right. Now I can run this, and I can check this function too. So this function is called prime counter A, and you'll see there are, how many primes are there up to 23? There's 1, 2, 3, 4, 5, 6, 7, 8, 9. So what we're going to see is if I call this function, initially there's going to be 0 primes, and then there's going to be 1, then 2, then 3, etc. up to 9. There's going to be some repeated values. But let's print the result of calling the function. So I'm going to say prime count array, and I'm going to give it my favorite prime again of 23. And when we save this, and then we run our code, what we'll see is this array that keeps track of them. So at n equals 0, there are 0. Then there's still 0 at n equal 1. We encountered the first prime, which is 2. So we've seen 1 prime. Then this is 3, so we've seen another. At 4, we haven't seen another one. At 5, we have. At 6, we have not. At 7, we have, and so forth. So this is keeping track of how many primes we've seen up to this point in time. That's obviously hideous if I tried to run this on 2300, right? So if I save this and run it, okay, this is going to be hard to work with. But at least we know that up to n equal 2300, there's 342 primes, if that's useful. But I don't want to do such a thing. What I want to do is graph this. So I want to connect the dots. I want n to be on the x-axis, and I want these values to be on the y-axis. Okay, so I'll clean up main.py there a little bit. And here's what's going to motivate us to view this as a graph. And if we're going to graph the primes, we're going to use the standard plotting package of Matplotlib. So that means that the first thing that we need to do is to install it. If we're installing Matplotlib, because it's external to the built-in installation that you have with Python, sometimes you have things like time or math. Those are very standard, and so they're included with your installation. But there are these other modules that you're going to want to install as packages on top of your built-in operation, or built on top of your built-in installation. And so if you want to install those additional packages, you're going to use the Python package installer, which is called pip. It comes installed with Python. And so the standard command for installing any package is either pip3 on a Mac or just pip on a Windows machine. And you can do this in the command line at any point in time. I'm going to type pip3 because I'm on a Mac. I'm going to type the word install, and I'm going to type matplotlib. Matplotlib. When I hit enter, it's going to go through the process of installing that. I already have it installed, so it's going to check that, and it's not going to show a lot. When you run this, it's going to go through the process of installing everything, and if you have your Python installation set up in the way that I suggested, everything is going to proceed automatically, and you'll come back to the command line when it's finished. If that works, the only thing that remains to do now is to go to our import statements and to import Matplotlib. Okay, except that I want to import a very specific thing. I want to import part of Matplotlib, and what I'm interested in is pyplot. So this is like a sub package of Matplotlib, and it's going to be very annoying if I have to, every time I call a function, I'm going to have to call matplotlib.pyplot. Whatever function I'm using. In the same, that was easy with math.squirt or with time.time, but with this is going to be a lot of stuff to type. And so for that reason, you can provide like an alias of what it is that you want to call this package, and I'm going to call it just pyplot. So a nice feature of Python is I'm not going to keep referring to it as this. I'm just going to call it by the name pyplot. Now that I've done that, I've got the import. It's just a matter of writing a function. I'm going to have a function that's going to use all this stuff, and it's going to produce a plot for us. So the function that I care about is going to be called plot primes. Now, this plot primes function is going to take an integer n as input, and it's also going to take a step as input, and I'm going to explain that here in a second. It's not going to need to return anything. It's just making a plot for us. And so I'm going to say our parameters are going to be an integer n and an integer step. Okay. And this function is going to plot as a line graph, where I'll leave it at that. So I'll say plots the number of prime numbers as a line graph, and then this is going to have as output nothing produces plot. So I'll be a little more precise about what the function does, where the xy on the graph corresponds to x is equal to some integer k, and y is equal to the number of primes encountered up to and including k. So the height of your point is going to correspond to how many primes you've encountered up to this point on the x-axis. Then we're going to just connect all of the dots. And here is our first foray into using Matplotlib. So the first thing I might do is, well, I could check that n needs to be not less than 0. That would be bad. Okay, and I'll actually, just for the sake of time, I'm also going to check if the step value is less than 1. Okay, so I should specify what the step value is going to be, because this makes a complete doc string. So to make this complete doc string, I'm going to say where we skip every step x values for some step parameter. Okay, so I'm not going to connect every single tiny little point. I'm going to jump, and I'm going to only plot them. A standard value of step that I'm going to use is going to be equal to 100. So the first thing I want to do is I want to call the prime count array function that I just wrote. So I've got a function that is going to keep track of how many integers are prime up to the current point in this array. So for element k in this array, it's how many primes are up to and including k. And I'm going to put that into something called pi. The reason why is the function for the number of primes up to and including n, k, is called pi of k. Okay. This needs to be after my value error checks. And once I've got that, so this is, again, this is a list corresponding to what we just wrote. Once I've got that, Matplotlib wants to know what are your x values going to be and what are your y values going to be. So we're going to make lists of those values. And I'm going to say my x values, x underscore values, starts off with an empty list, and then I'm going to add values to it. So the x values are simply going to be all the values of k where we increase by the step size each time. So it's not quite just saying x is 2 and then 3 and then 4. It's going to be x is 2 and then 2 plus the step, and then 2 plus the step times 2, and 2 plus 3 times the step, and so on. So I'm going to say for x in the range of 2 going up to n plus 1 with the step size that we indicate, I'm going to go into the x values. I'm going to append the current value of x. Okay, so this is the current value of k I care about. And then I'm going to say make our list of y values by setting y values equal to an empty list. And now I just need to say, what are my y's? Well, my y's are, for a given x, the y value is pi of x, the number of primes that I have encountered thus far. And I already know what that is. I can just access it from the list that I made. So I'm going to say for all of the things in the x values that you encountered, okay? So for every x, there's a y. I want to append to the y values the corresponding value of my list. And I'm calling my list pi. So it's just pi of x. So pi of x is going to store the height of what I want this point to have. Now that I've got the x and y values, it's just a matter of plotting. So now we're going to plot. And here's where we're going to use all of our built-in pyplot functions to help us. I'm going to set pyplot.figure. So this is going to create an initial figure for us. And this initial figure needs to have a specified size. So when I specify my size, I'm going to say that the fig size is equal to 9 and 6. Okay. So this is 9. This tells me the width and height in inches. Okay. As you may know, I'm no fan of the metric system, so I'm glad that this defaults to inches, a better measurement. And then we're going to create the plot itself. So the figure, think of this as like the canvas that we're going to draw on. And then we're going to set pyplot.plot. And here's where I give it the x values that I just made, the y values that I just made, and I need to give the plot itself a label. So the label, and this is going to look very technical, but I'm going to say label equals r, and then a string that's going to store what I want the label of this plot to be. And so the label that I want to use is called pi of n, the prime count. Okay. And so that's, by label I mean this is going to be in the legend. I'm going to have a separate command called pyplot.title that's going to be called the prime counting function, pi of n. And then I'm going to label, because I'm a good scientist, what do we have to do? They always tell you have to label the x-axes and the y-axes. I'm not sure why, but we're going to do it anyway. So the x-axis is going to just have n. The y-axis is going to have this pi of n. And then I'm going to say I want a legend. So pyplot.legend, that will draw the legend. I'm going to have one more function called pyplot.tightLayout. This will ensure that it's automatically resized. So it'll like fill the chart, for example. And then I have one more, which is pyplot.show. And this says we're ready to draw. Okay. If we make it there, we're going to plot the plot. So here is our function that will plot the primes. And notice what's going on behind the scenes. There's a lot of function calls that are just automatically happening for us, right? So I called prime count array, and behind the scenes, prime count array is doing what? Well, it's also calling the sieve of Eratosthenes, and the sieve of Eratosthenes is going behind the scenes and is calling cross-off multiples a lot. And now we're starting to make the transition towards what we're going to do as we move through the class, which is that any individual function that we write isn't necessarily going to be that long, but the functions are really going to work together quite a bit. But in this case, what I really want to do is complete this by calling the function itself. So I have my function that I just wrote called plot primes. I want to give it a couple of possible values. So let's give it a value of, I think n might already be 20,000, but let's set n equal to 20,000, or let's make it a power of 10. And let's set the step equal to 100. And I'm using sieve of Eratosthenes. We may as well make it 100,000. And now I'm going to call my function, which was, I called it plot primes. Remember, it does not return anything. It just takes my n, and it takes my step. Hopefully this works. I'm going to hit the up arrow very cautiously. Oh, I don't want pip3 install. I want python 3 main.py. And then I'm going to close my eyes and hit return and hope it works. Okay. So now we've got a plot. I probably should show you the plot. And here is my plot. So this gets produced as a result of running the code. And here is our nice pretty figure that's showing me for a given value of n, what are the number of primes, pi of n, encountered up to that point in time. The question though is, what is this a graph of? What does this look like to you? One thing I might do while you're telling me what you think it looks like is increase the size of n. Okay, so let's do that. It looks linear, right? Yeah, it looks linear. I like this answer. I agree. It almost looks like, is that even right? That it would be linear? But then wait, not quite. It's not quite linear. You can see at the start, it's not quite linear. So let's give it a bigger value. Let's give it not 100,000. Let's give it 10 million. And let's save. And let's run it again. And then when this completes, it's very fast because sieve of Eratosthenes is very fast. And again, it looks linear, but it's not quite linear. All right. And you know enough, actually, I'm going to show you another graph here. It turns out if you try to fit a line to this, it looks pretty close. But the problem is when you add the line is probably going to shoot underneath this graph, and then eventually it's going to intersect, and then it's going to go above it. And that's not good, because what that means is there is a curve here, but it is very subtle. It's very subtle. So the question is, what are we missing here? Right? And in other words, also, what is it that is a good fit for this? And we've heard that there is another function that this is similar to that we can look at. So the other function that is, it turns out, that it's very similar to is, I should say, pi of n. It's very similar to n over the logarithm of n. Okay, so n over the logarithm of n here, where the logarithm is the natural log with a base of e equal 2.71828, 18284, etc. All right. So let me do something, which is to add the graph of n over log n to my plot and just see what happens. So I'm going to add in another set of y values, right? So I've got my list of y values here. And so let's have another collection of y values corresponding to n over logarithm of n. So I'm going to set y values, and I'm going to call this y values approximately is equal to an empty list. And now for x and x values, I'm going to append x divided by math, which I've already imported, dot the logarithm of x. So here's where I'm going to have my x divided by the logarithm. Okay. Now, we've ranged through the x values. We know what our x values are supposed to be. And here is our approximation function, which is x over math dot log of x divided by the logarithm of x. And now I've got this collection of y values. I just need to add it into the plot. So in the plot section, I've got the x values here. I've got the y values as well. But I also want to add a plot for the n over log of n function. Okay. So I'm going to say pi plot dot plot also the x values against the y values approximate. And the line style that I'm going to have is going to be dashed. So I'm going to indicate this is a dashed line, which I didn't specify before. And the label that I'm going to have is going to be, I'm going to remove this r here, n divided by log n. And then finally in the title, I'm going to say I'm plotting pi of n, and I'm going to plot it against n divided by log n. Now when I save this, and then I run, well, I guess the first thing I should do is to close out my plot. That's going to end the program that I was running. When I save this, and then I run it again, now it's going to add my n over log n to the plot that I have. And what you see is that this is not quite a perfect approximation, but it's definitely close, and it's following the same type of curve. Okay, so what we have is that the values are not perfect, but one of the things that's nice about this is that as n continues to increase, so as we continue to go out towards the left, that gap between the functions is still going to remain, but it's not going to increase at a very great rate. So the functions are still going to remain tight against each other. as you may know, I don't know if I've mentioned it, but I do have an MBA. And so one of the things that we saw last time is that whenever you have two values that you're interested in, sometimes the smartest thing to do is to take the division between them and to take the ratio and compare them. So it turns out that when you look asymptotically, so as the numbers get really big, as n goes off to infinity, and you take the ratio between the values of the number of primes that you've encountered up to a current point in time, and this n over log n function, and you look at what you wind up getting, here is the math package I was going to show you, by the way. So here is, we can see our a lot of different functions that we have. So if we look at log, like if you just take logarithm and you don't specify the base, then you're automatically going to get e, or the natural log, by default. But we also have what's called the prime number theorem. And the prime number theorem is another mathematical result. And that is a verifiable, hard statement in mathematics, which is that if you take the ratio of these two things, the number of primes that you encounter up to a given integer n, and then this function, n over log n. So you take the ratio, then as you get bigger and bigger, that ratio goes towards 1. All right, and this is based off of a lot of work from Riemann, as well as two people you never will have heard of. We've got Jacques Adamar and Charles Jean de la Vallée-Poussin in 1896. Two people who independently discovered this amazing thing, and then the average person doesn't even know what the statement of this amazing theorem is, which is that the number of primes essentially grows like n over log of x. There are better approximations for it. So it turns out that as you go out asymptotically, there's this other thing that gives you a tighter approximation because the ratio gets closer to 1, which is the integral of 1 over the natural log of t. But we were not going to take that divergence because this is just a matter of going back to our picture and trying to make the gap between those functions a little bit tighter. It turns out you can approximate it with a slightly different function. But the idea that the ratio between them goes to 1 is a very powerful result and wasn't even established. This is called the prime number theorem. It wasn't established until nearly 1900. And here's our visualization of it that we were able to produce. Now, there's another point, though, as we wrap up. There's another point, which is I've already seen the mention of specific examples of the largest prime. And the largest known prime number, I'd be impressed if you knew what it is, but as of this moment in time, it is a number that has over 40 million digits. It's 41,024,320 digits when represented in base 10. The chances, one of the nice things about this is when you have the prime number theorem, right, it's on its own, it's a beautiful statement, right? It's a great example of the human spirit going in and proving something very complicated that winds up having a relatively simple statement that people can understand. That's awesome. But it also has ramifications for prime finding. And one of those ramifications is you can prove as a result of this that if you go out for a certain number n and you say, I'm going to pick an arbitrary number n, what are the chances? I'm going to draw an integer out of the hat. What are the chances that this number n is prime? It turns out that once you have the prime number theorem, it allows you to say that that chance is like about 1 divided by the logarithm of n. So that's not a very tiny number for values of n that are like 100. So because we see lots of primes. But what happens is that over time, what you were seeing that looked like a line, and I see in the chat, folks are still trying to fit a line to this. And I would say, well, don't plot y equals x, because that's very wrong, okay? You're going to need a different slope than that. But you could plot something like, I don't know, y equal 0.7x or something. And for the first few million primes, it might look kind of similar. But the problem is that eventually, this curve really does curve to the point that it becomes very rare for you to encounter new primes. So when I say that and when we work with numbers that are this large, the chances of drawing a number with this many digits out of a hat that it would be prime are about 1 in 100 million. So the primes really do get very sparse. We start to run out of them when you start looking at huge numbers. And that's an issue because even if you happened to draw out of a hat with this amazing chance, this amazing 1 in 100 million lottery pick that you picked a number, even establishing that that number is prime is hard. That number is so big that it has to be part of what's called the Great Internet Mersenne Prime Search in order to even demonstrate that that number is prime. This is a huge, very complicated mathematical algorithm that is run on a lot of different contributors' machines. So it's an example of a parallel algorithm that's distributed across a bunch of different machines. And if you're the person who finally demonstrates it, then they give you credit because you contributed your compute to it. We're going to talk more about parallel programming and distributed computing much later in the class. But for now, I want you to notice that this number just happens to be 2 to some particular number, 136,279,841 minus 1. Gee, that's a funny pattern, that it just so happened that they found that the largest prime has this form. And the reason why is because numbers of this form, 2 to the n minus 1, are not always prime, but they're more likely to be prime than like 1 out of 100 million. So the likelihood that this particular number is prime, because it's of the form 2n minus 1, for whatever reason, is just much higher. And those particular types of primes are called Mersenne primes. So, named after yet another mathematician. We have a whole section of practice exercises in the meantime that you can work on as we've wrapped up Chapter 0. And some of them are on Mersenne primes. So it turns out these Mersenne primes are connected inherently to yet another collection of numbers that the Greeks were interested in. And if you're interested in working with this, I'm not going to make you find 41 million digit prime numbers, but I am going to give you the opportunity to explore some of these connections between numbers that the Greeks cared about and these Mersenne primes. And now that we've reached the end of Chapter 0, you know plenty, and you just have to go and do it. So we've learned a bunch of math. That concludes what we're going to do with Chapter 0. We're ready to now take the next steps and complete some applications on a lot of other different scientific topics. That's going to wrap up what we're going to talk about tonight. I'll see you next time. And in the meantime, happy coding.